Welcome back everyone. Last lesson we saw multiple regression. Now we're going to logistic regression, which is not really regression, but it is at the same time. Well, I'll explain later. In the previous regressions models, we predicted numbers like house pricing or I don't know, Pokemon stats. So here in logistic regression, we don't predict a number. So actually it is a classification model and it's gonna return us a probability. And the probability will be within the range of 0 and 1. 0 being false and 1 being true. So basically when we're looking at our target and we need a probability as our outcome, we use logistic regression usually, okay? There are many types of classification as we're gonna see later, but let's start by logistic regression. So why is it regression? And it's kind of that together within the regression but classified at the same time, because the equation is the standard linear equations. So y hat is equal to theta 0 plus theta 1 and our features. But in a linear regression model, the line goes to infinite, and we don't need it here because we need a yes or a no, so it's kind of a binary choice, right? So basically what we do is we calculate in the linear equation, but we pass in the sigmoid function, so it kind of that compresses the number within the range of 0 and 1. It's not a straight line going to infinite anymore. It's going to be a line between 0 and 1, which are going to be our probabilities. So there are a couple of applications here, such as prediction heart attack or the probability of failure of a given process or a given system or product. We can predict the chances of a specific disease appear in a person and actually any likelihood or any probability. So in training here, we gotta identify the parameters that will minimize errors as most of the models, but here you're gonna usually be using either gradient descent or the stochastic gradient descent. So there are techniques that iterate through the data set and find the best coefficient by testing some random values into the coefficient. We can try to speed this process by increasing the learning rate, but if you try to speed this process, you gotta be careful, because maybe the step might be too big, so the model might miss the greatest parameter, which is when our model converges. And we have a variation of gradient descent, the stochastic. What basically does is that it uses a subset instead of the entire data set. So gradient descent will be using the entire data set, iterating and testing values to find the convergence point, and the stochastic uses a random subset. It converges quickly but can be less accurate. So we want to use this when our data set is really too big. Let's jump to our code. Basic imports, pandas, MPI, skitlearn, we already know that. Let's take our data set here. I changed the data set actually, so I'll explain the data. We'll be predicting the probability of a character defeat a boss in a RPG game. Let's load the data and visualize it. So this data we have 7 columns and 1000 rows. So let's take a look at our observations. I have some stats here, player stats, and we have the player class, and fboss is the probability of defeating the boss. It's a boolean, true or false. Let's say here in the first row, a magician with these stats, it will defeat the boss, and so on. So our features will be everything excluding fboss, but you gotta be careful because our class is a categorical column and we cannot do statistical computation with strings. Like our model don't know what magician means or what warrior means or tank, so we gotta convert it to numerical values, our class column. To do that, we can check how many classes we have here, how many classes of our RPG game, for example, and we can do that by running value counts. So we can see that here we have 6 classes and they are well balanced. We can see by the rate of appearance here, none of them appears much more than others or much less than others. So we can convert that. We can use this PD get dummies, but it doesn't save the model, right? So we can use either dummies or the best practice will be using one-hot encoding. Okay, it's a library we can port. It does pretty much the same thing, but it saves. So if you add another class here, the code won't crash. We can do that, and we can run our data frame. We see that instead of having the class with strings, we have them separated, and now they are booleans, so they are numericals. For the first one, which is mage, our magician, we have 1 for magician and 0 for others. And you might notice that we only have 5 here, 5 columns, and actually we have 6. Why is that? Because we pass a drop first through. It's usually a good practice to do that because it's gonna avoid correlated features. Basically what it does is that it's gonna drop one column of the D6 and use it as a baseline. So for example, it dropped battle mage in this case, and this row where the player is battle mage will be 0 for all classes. So it's intended that this character is a battle mage. We can run a scribe just to see the statistical values, numbers. We gotta standardize it, but we're gonna do it later after split and train, because we usually scale our data after splitting and training. So let's track that our feature and our target here. Feature is basically everything excluding FBOSS, so we just drop it. And for our target is just FBOSS. Now we gotta split it into training and test sets. Then after splitting, we will scale it. And why is that? Because we don't want to scale our test set, okay? We don't want to pass fit to our test set. If you scale here before splitting and training, it will be kind of that cheating. Our model will be kind of that cheating because theoretically, our model shouldn't know that our data is scaled in the unseen data. Then we can initialize the model, logistic regression model, and pass the standardized set, the training variable, and we can run the predicted. So after training the model, we can predict it right here using the unseen data, the simulated unseen data, which is our test. We run that, and then we can predict the probabilities. Okay, it's gonna be our white hat probabilities, and we can display our probabilities of defeating the boss or not. The left column is for 0 and right column is for 1. 1 is basically yes, we're defeating the boss, and 0 is no, we're not defeating it. Something cool we can do with logistic regression is that we can plot a horizontal graph to see the kind of the wave of each feature, like or how much each feature influences toward our target variable. We just plot the graph and we just label it, and I'm gonna just sort for lowest to highest values. If we print that, we can see that magic, physical, and weapon has a really high influence in defeating the boss, while armor and level is almost irrelevant. So if you were the game designer, for example, of this game, we could see that our game is really unbalanced. Magic is really overpowered, physical and weapon as well, so level doesn't influence that much. And these classes here are kind of weird because they're comparing the battle mage, because the battle mage is our baseline for these encoded columns. So typically choosing sorcerer, tank, magician, and warrior are better than choosing battle mage, but knight typically gets a lower win rate when it comes to defeating a boss than the battle mage. Now we can visualize the log loss. We can visualize the log loss on test and on train set. If they're different, and it could be a problem. Our model could be overfitting. They're really similar and they're really low. Active value is too low of loss. Are kind of worrying because it's too perfect to be true, you know. So it's good to run our log loss on test and train set, and it's good to run the accuracy as well. So with these values for loss, our accuracy should be high as hell as well. Yeah, it is high. So our train set accuracy is 80, 98% and 97%. But this is fine because our database here is really simple. It's already cleaned and prepared for these kind of tasks of training machine learning models. Really simple one. now that you already know the code in general here, it's gonna be easier to explain, okay? That's it, guys. Thanks for watching, and see you in the next video.